Our next concept is using inertial navigation. Basically, we've known previously that we need to know our pose, our position, orientation within an environment. And in relative positioning, we add up all these incremental changes in position and orientation to determine what our pose is. Well, using inertial navigation or inertial navigation systems, INS, we measure forces on a system. We measure forces related to rotation and forces related to linear movement. And based on that, we can add up the distance traveled by these forces and navigate around and estimate where we've moved to. So we've got two different things that we're available to us. One, we've got gyroscopes that allow us to measure rotation in a particular axis. And we've got accelerometers, which allow us to measure planar movement or positional change within an axis, or the force associated with that. We've got a few different types of gyroscopes. We'll turn our attention to accelerometers in a moment. But the three main types, we've got the mechanical ones, lasering ones, and MEMS ones. So let's look at what they actually are. Now, the basic mechanical gyroscope involves a rotor that's quickly spinning around one axis. Essentially, the faster our rotation, the more resistant it is to attempts to change its axis direction. And we typically mount these inside two gimbals, so it becomes really obvious. So we spin them up really fast, and if we have rotation perpendicular to the direction it's spinning, this is what we call the input axis, the gyroscope will rotate in the output axis. And so we see the input and output axis there. One very primitive way that we can think about gyroscopes is we think about these things, which has been all the rage for a little while. If we spin them up and have them going quite quickly, we notice as we try and turn it, essentially changing its input axis, we feel forces in other axes, and particularly as we turn it one way, we actually feel a force that's occurring in the output axis, as per the diagrams that we've got there. Spin it around. If you've got one of these, try it out and have a bit of a feel about it. These mechanical gyroscopes are what we term the original gyroscopes, and they've been around for hundreds of years. So developed in 1743, these were essentially an instrument we used to locate the horizon when in dense fog, particularly used in shipping. They were based on the design of a top, and spinning tops have been around for thousands of years, mainly as a kid's toy. And that brings us to the next type of gyroscope, which is a lasering gyroscope. These are very, very accurate, but also very expensive as well. And they have no moving parts, as opposed to the mechanical gyroscope. That can be one issue with the mechanical gyroscope, that we might be developing a platform where we don't want the gyroscope to be turning very quickly and resisting the motion that we're trying to move in. For example, if we're developing a UAV. Now, these are based on the Sagnac effect. This is named after a French physicist, Georges Sagnac. And basically the idea is that we have a light source and we split that light source and send it in two different directions. So one direction, another direction, and then we have a detector where we measure the phase difference between these two light sources at the end. Now, the phase difference, the phase will change if we've had rotation occurring. So one of the light paths, if we've had rotation occurring, will actually travel a longer distance than the other light path. And based on this, they'll be detected as out of phase by a certain amount from each other. Now, rather than using mirrors like we've got in this example, we can use optical fiber and a ring of optical fiber to allow this to occur as well. And so we're basically looking at the magnitude of this phase change to determine how far we've changed in one direction. And this is what we'd term as a one-axis lasering gyroscope. And we could have these in multiple axes. The next type of gyroscope is a MEMS gyroscope. And this operates on the principle of vibration. So a vibrating object will continue to vibrate in the same direction, the same plane generally, as its support rotates. And so we rotate and we see this vibration occurring, and we can measure this vibration. MEMS stands for micro electromechanical systems, and these are tiny. So we're talking about something much smaller than a grain of rice, and we can very easily build up systems of 9-axis gyroscope and accelerometer and magnetometer and things like that, all in a single little chip. Typically they're in these tiny little packages, and they're very, very inexpensive, particularly compared to lasering gyroscopes. We're talking tens of dollars at the most, and they are susceptible to drift and noise over time. Now, these are very commonly used in consumer electronics, Wii remotes, smartphones, laptops, and also in robot navigation, particularly on the small sort of scale. And that brings us to accelerometers. We've looked at a few different types of gyroscopes where we're measuring rotation around a particular axis. Accelerometers allow us to measure acceleration in a particular plane. Now, if we put an accelerometer on the table and just allow it to measure gravity, it will measure 9.81 meters per second. If we turn it upside down, it will measure minus 9.81 meters per second, as we'd expect. If it's in free fall, if we throw it out the window and it hasn't reached terminal velocity, we'll be getting 0 meters per second because it's in free fall. And this is what we use in laptops, for example, to detect if a laptop's fallen off a table, and we can stop the hard drive and remove the head to avoid a head crash when it hits the ground with a rather big thump. Now, we can use INS systems to significantly assist and improve our odometry. We've previously found that odometry tends to drift and get worse over time because these small errors are accumulated over time. Particularly a small error in the angle or the orientation that we think the robot's in. This will increase and lead to a much bigger path error over time. So one solution is, rather than using the odometry to work out what our error is, we use the INS system or a magnetometer or something like that to measure what our orientation is and compute our distance traveled using the odometry. Having said that, gyroscopes also drift with time, and generally not as badly as odometry, but they do drift with time, and so this is something that we need to take into account. And we'll look at techniques in a moment to do so. So there's a few different ways that we can integrate INS in with odometry. One of them I mentioned is use odometry for the distance and the INS system for the heading or for the orientation. We can use odometry for distance and take an average between the odometry and INS value, maybe a weighted average for our heading or our orientation. Or gyrodometry. We use wheel odometry for our primary navigation and gyroscopes when a bump or some sort of spurious reading is detected. And I'll show you in a moment a scheme that we can use for doing that, and it significantly improves our performance. Here's a diagram showing how we can use our INS for improving our heading. So here we use the odometry just for the distance and the INS for the heading. In the top diagram, we see using the wheel odometry only, and we see before very long, before many cycles going around this path, our heading is way off, resulting in huge errors in our navigation. Using the INS though for the heading, we see that we've actually stayed pretty close to where we need to be, and we've got pretty decent performance out of this. When we analyse the sort of system accuracy and error that's occurring, without our IMU being used and just with our odometry, we have significantly high error in terms of number of millimetres we're out from where we actually, for our known position. But when we use our INS in there, this error is kept to a much, much lower level. Now, one thing that we need to think about as well is how acceleration, velocity and distance are related to each other. They're related over an integration relationship over a certain time interval. So if we integrate our acceleration, we are given velocity, and if we integrate our velocity, we're given distance. And likewise, if we differentiate distance, we can get velocity, and if we differentiate velocity, we can get acceleration. So these accelerometers can be used to compute both distance and velocity from the acceleration value. But one thing that we need to note is we're integrating these values twice, and so we're introducing significant errors in there when we calculate our displacement based on our acceleration. Now, there's some circumstances where rather than using our INS with odometry to supplement it, it's the sole thing or the primary thing. And in this sort of circumstance, we might not have wheels to deal with, like for example an aircraft or a boat. Or if we know we're on a very slippery surface and wheel odometry is just going to be poor anyway, or if we've got a omni-wheel robot that relies on slippage to occur, INS might be a better situation to occur in that particular case. and we'll be using our gyroscope to give us our heading and our accelerometers to give us our linear distance travel, our movement. Now, I mentioned this concept of gyrodometry before. Now, odometry typically handles these non-systematic errors like bumps and slippage very, very poorly. But gyroscopes also have this issue that they drift badly over time. And so for short time intervals, with no bumps, our odometry matches our gyroscope quite well. And so we can use an algorithm like this. Over our short time interval, if our wheel odometry matches our gyroscope-derived heading or our orientation well, we'll use our wheel odometry. We trust that, and this will avoid and remove the drift that's introduced by our gyroscope. But if they're significantly diverging, we'll assume a non-systematic error has occurred, a wheel slippage or a bump or something like that, and then we use our gyroscope data for our orientation. Now we can see in the diagram there, if we just use our wheel odometry, our error in our orientation increases very, very substantially, very, very quickly. If we just use the bottom line there, our gyroscope, we have the error not being as great as what we had for wheel odometry, but still increasing over time. If we use this sort of scheme, gyrodometry, we can keep that error much, much, much smaller compared to either of those other ones. So as we close off about INS sensors for the moment, we have lots of applications for INS sensors beyond robot navigation. We use them in balancing robots, for example, like in segways, and for things like computer hard drives and detection of drops and bumpy environments. We use them in aircraft for attitude feedback, and mobile phones is actually an input device where we can have games and things based on the movement of our accelerometer and gyroscopes. And in our Wii controllers and game controllers and things as well.